Welcome, future pilots. If you're currently studying for your private pilot license ground exam, you already know there are a few heavy aerodynamic topics that can, well, really trip you up. Today, we're going to master one of the absolute most critical concepts you'll be tested on, and that is aircraft stability. We've distilled the complex physics into a clear, visual explainer so you can walk into that exam room with total confidence. Let's get right into it.
But hey, before we dive into the heavy aerodynamics, here's a quick question to loosen things up. Why did the airplane break up with the helicopter? Because it just needed some stability. Okay, dad jokes aside, finding that balance really is the absolute core of what we're looking at today. To make sure you totally nail these concepts on your exam, we're breaking this down into 5 logical buckets. 1. The basics of stability. 2. Static versus dynamic stability. 3. Pitch, or longitudinal stability. 4. Roll, which is lateral stability. And 5. Yaw, known as directional stability. Okay, section 1. The basics of stability. Setting the foundation. Let's lay the groundwork for what this actually means when you're up in the air. So, the crucial point here is a classic exam trick. You have to understand the trade-off. Stability is an aircraft's inherent design quality to correct for conditions that disturb its equilibrium. It naturally wants to return to its original flight path. But here's the catch. This directly fights against maneuverability and controllability. Maneuverability is the quality that lets the aircraft be easily moved and withstand stress, while controllability is how well it responds to your pilot inputs. A training aircraft is designed to be highly controllable and quick to respond. A massive transport aircraft, on the other hand, is built for maximum stability. That means it feels much heavier on the controls and responds more slowly. Essentially, the more stable an airplane inherently is, the harder you have to work to maneuver it. Moving on to section 2, static versus dynamic stability, the core difference. Let's see how aviation engineers categorize an aircraft's reaction into 2 highly specific timeframes. Think of static stability as the immediate initial reflex of the airplane, the very split second after a gust of wind hits it or after you bump the yoke. It's just that initial tendency. If it has positive static stability, its first reaction is to try and return to where it was. If it has neutral static stability, it just happily stays right in the new disturbed position you bumped it into. And if it has negative static stability, well, its initial tendency is to keep moving further and further away from its original balanced state, which is incredibly dangerous. As a pilot, you definitely want an aircraft designed with positive static stability. Now, dynamic stability, on the other hand, is the aircraft's response over a period of time. Let's look at how positive dynamic stability actually diminishes oscillations. Imagine a gust of wind suddenly pitches your nose up. Because of gravity, your airspeed drops, which decreases lift, causing that heavy nose to naturally fall into a dive. As you dive, your airspeed increases again, creating more lift, which pushes the nose back up into a climb. But this time, the climb is slightly less steep than the first one. Through a series of these gradually shrinking waves, which aerodynamicists call damped oscillations, the aircraft eventually settles back into perfectly balanced, straight and level flight all on its own. All right, section 3. Pitch, or longitudinal stability. Let's move to our first specific axis of flight and see how design directly influences pitch. Now, longitudinal stability is a term that trips up a lot of students because it sounds, slightly counterintuitive. It prevents the aircraft from endlessly diving or climbing. But it actually describes stability around the lateral axis. Just picture an invisible line running straight through the aircraft from wingtip to wingtip. Longitudinal stability is what controls the pitching motion up and down around that wingtip to wingtip pivot point. Without it, an aircraft could easily pitch progressively into a steep dive or a dangerous stall. So, if you get a ground exam question asking what keeps the nose level, you want to look for these 3 specific design factors. It depends entirely on the location of the main wing in relation to the aircraft's center of gravity, the location of the horizontal tail surfaces in relation to the center of gravity, and finally, the total surface area of that tail. Let's look at how those factors actually work together in the sky. Most aircraft are intentionally designed so that the wing's center of lift is slightly behind the center of gravity. That makes the aircraft naturally nose-heavy. To compensate for a nose that constantly wants to drop, the horizontal stabilizer at the back is set at a slight negative angle. This creates a downward aerodynamic force on the tail. This setup acts exactly like a seesaw or a lever. The downward pressure on the tail perfectly balances the heavy nose, keeping you in straight and level flight. Plus, when your speed increases, the air rushing over the wings creates a stronger downwash that hits the tail, pushing it down even harder and pitching the nose up to safely scrub off that excess speed. It's an incredibly clever self-correcting system. Moving right along to section 4, roll or lateral stability. Let's explore what keeps the wings from just flipping over. We're now looking at lateral stability, which is stability around the aircraft's longitudinal axis. So imagine an invisible line running from the spinner on the nose straight through the fuselage back to the tail. When turbulence knocks one of your wings down, lateral stability is the invisible force that rolls you back to level flight around that nose-to-tail axis, completely preventing an accidental spiral. You absolutely need to commit these 4 terms to memory for the test, as they are the primary engineering tricks used to prevent an unwanted roll. We've got dihedral, sweepback, keel effect, and weight distribution. With keel effect and weight distribution, the aircraft is essentially built so that the majority of its side area and weight act kind of like a pendulum. When a wing dips, the heavy fuselage weight naturally swings the airplane back to its original attitude. But the most common design feature you'll see on training aircraft is dihedral. Dihedral is the slight upward V shape of the wings when you look at the airplane straight on from the front. Let's walk through the step-by-step process of how that V shape automatically saves your attitude. Imagine a gust drops your left wing. The aircraft instantly starts slipping sideways, downwards toward that lowered left wing. Because the wings are angled up in that V shape, the relative wind from that sideways slip strikes the lower wing at a much higher angle of attack than the raised wing. That greater angle of attack instantly generates a surge of extra lift on the lower wing, which powerfully pushes it back up until the wings are completely level and the sideways slipping stops entirely. And finally, Section 5, yaw, or directional stability. Let's tackle the third and final axis, which keeps the nose pointing exactly where you want to go. Directional stability is stability about the aircraft's vertical axis. Just imagine an invisible pole driven straight down through the center of the cabin. When the nose swings left or right around that pole, that's called yawing. You can think of directional stability as the airplane's built-in weather vane, ensuring the nose always wants to point straight into the relative wind. So the crucial point is how we actually stop the plane from flying sideways. The vertical fin acts exactly like a feather on an arrow. For this weather vane effect to work properly, the side surface area of the plane must be much greater aft, meaning behind the center of gravity, than forward of it. If the fuselage area and vertical fin behind the center of gravity weren't larger than the front, the aircraft would literally try to spin around and fly backwards. Sweepback wings also provide a minor assist here. If the plane yaws to the right wing suddenly presents a longer leading edge to the wind, increasing its drag, which smoothly pulls the nose right back to the center. Okay, to pull all of this together, I highly recommend taking a quick screenshot of this cheat sheet right now. Matching the axis to the resulting motion and identifying the exact design feature that stabilizes it is virtually guaranteed to be on your exam. Remember, the longitudinal axis is the pivot for pitch, stabilized by the horizontal stabilizer. The lateral axis is the pivot for roll, stabilized by dihedral. And the vertical axis is the pivot for yaw, stabilized by the vertical fin. Ultimately, understanding that the aircraft is inherently designed to actively correct itself is going to give you incredible confidence to fly smoothly. You don't have to fight the plane. It literally wants to fly straight and level. Trust your airplane's stability. Thank you so much for joining me today. Please hit that like button and subscribe for more targeted flight training explainers to help you ace your ground exams. But right before you go, ask yourself this. If the plane naturally wants to fly straight and level, how much of your current flying is actually just you over-controlling the yoke? Think about it, and I'll see you in the skies.